is for our winding voltage. Okay? So, what is our primary winding voltage?
120.
Primary.
480.
Mm-hmm. Alright, so that turns ratio 4 to 1. Our secondary winding voltage is going to equal our primary winding voltage divided by 4. So in our Y secondary, we have a winding voltage of 120 volts. So what would be our secondary line voltage? 120 is our winding voltage. Remember, this is a Y secondary. So voltage is going to change, right?
E winding times 1.73.
Right, it's going to be the line volt or secondary. It's going to be the winding voltage times 1.73, which will give us 208 for our line. All right, so hooking this up. All right, notice all of our X2s for each winding are all tied together and going down to neutral. All right, X1 going down to A. X2 on this one, or X1 on this winding going down to B. And X1 on the far winding will go to C. Now, anytime you see on a wiring diagram like this that one side of a winding is tied with all the other ones going to a common point, you know it's going to be a Y. Because all this is this right here. I know y'all have heard people call it neutral the common.
Yeah.
Well, I got a common point here, right? Does that make sense? Alright, so for our secondary line current,
So on a pole, this is where you're saying it comes from the neutral line to the pole ground to the ground rod.
yes. Mm-hmm. Alright, so next we need to calculate our line current. Same thing, KVA over our line voltage times 1.73. So in past classes, that's the thing that people's had the hardest thing keeping straight. If it's asking you for line current, you're going to use the line voltage to calculate that, right? Make sense, apples and apples, oranges and oranges. All right, so take a look at our primary line current. It's 180.6 amps at 480 volts. All right, on our secondary line current, it's 416.85 amps at 208 volts. Okay, if we do these calculations, if we take our line voltage times our line current times 1.73 on both primary and secondary, they have to equal each other. Well, what was the thing I told you, the most important thing you need to know about transformers?
Don't fucking worry about it.
No.
You'll take care of us.
No. one of the very first class we did on transformers. So, guys, this is the most important thing that you need to remember about transformers. KVA in has to equal KVA out. KVA in equals KVA out. And if you notice on our the current calculation here, we're using the same KVA on both of them, right? Mm-hmm. KVA in equals KVA out. Alright, so we got our line current. What's our winding current going to be on the secondary? It's going to be the same. Why is that?
Why?
Absolutely. Alright, y'all got that? KVA in equals KVA out. Alright, so now we have a Y primary with a primary line voltage of 4152, 200 kVA transformer with an 8.66 to 1 turns ratio and a Y secondary. Alright, so we know our line voltage on the primary is 4152. We'll divide that by 1.73 to get our winding voltage on the primary. So we got 2400 volts in each winding in this Y primary. Where's H1 going to go here?
Neutral.
We got an A. Where's H2 going?
Neutral.
No.
Neutral.
No. We're going to go to neutral. So why? Mm-hmm. If you follow your H2, going here, it's connecting up with B phase, then you connect up with C phase H2, and they're all going up to the neutral. Alright, line current equals KVA over line voltage times 1.73. And our winding current is going to be the same because it is a Y connection. Alright, so what is our secondary voltage going to be? Our secondary winding voltage.
E line divided by 1.73.
No.
Alright. Oh man, damn. Winding voltage.
Alright, so our secondary winding voltage is going to be our 2400, which was our primary winding, divided by our turns ratio of 8.66 to 1. It's going to give us a secondary winding voltage of 277. What will our secondary line voltage be?
E1 times 1.73. I'm just looking at the Y.
That's right. Yeah, I mean, y'all should be able to just know that shit.
Yeah.
Well, I know y'all seen panels that's got 277 and something else in it. What's the something else? 480. All right, same hookup as the primary. Then our calculation for our secondary line current. Alan, you got your calculator? Multiply our primary line current times 8.66.
241.0944. Or,
Pretty damn close to that right there, right?
yeah, very. Well, yeah. A little higher.
So we know that with transformers, it is a step down transformer. Your voltage is going to go down, but your current's going up, right? Because kVA in's got to equal kVA out. All right, so what's our secondary winding current going to be? It'll be the same thing. Y'all go with this? Y'all want to go through one more?
One more.
And y'all want to stay in class longer?
Hell no.
No. I mean, I'll do one more for my sake, but that won't be here as long as fuck no.
Let's do one more, and then y'all can do the rest of them along with your homework. Gary, what are you bitching about?
Man,
Everything.
Hey, Skip, is there any difference between X1 and X2? Like, if it's a Y, which one connects to the others?
X2 is always going to connect together. Your X1 is going to be where you tie your two. Now, you know, on the Delta, you know, it's a little bit different, right? Because they're not all tied together. Right? But yeah, with the Ys, your X1 is going to be your field side. Your X2 is going to be where they're all tied back to neutral. All right, we got a Y primary with a primary line voltage of 208. It's 150 kVA. It's a 1-to-2 turns ratio with a delta secondary. Well, is this a step up or step down transformer?
Down.
Step up.
It's going to be a step up. I'm just saying whatever the opposite of what Garrett says. Just, it is a step up, right? So, line voltage given is 208. So what is our primary winding voltage?
208.
In a Y configuration.
208. 208 times 1.73. No.
Divided by.
Yeah. That's right.
24.4.
Alright, so we got 120 at each winding in our transformer. Same connections. X1 to A, X2 to neutral. B phase X1 to B, X2 neutral. C phase X1 to C, X2 neutral. Alright, line current, 150K over 208 times 1.73 gives us a primary line current of 416.85. What is our primary winding current? Absolutely.
Yeah.
Alright, so turns ratio, 1 to 2. So, all we're doing when we calculate our voltage with a turns ratio is we are dividing our primary by the turns ratio. Another way to write the turns ratio is 1 over 2, right? So, we'll divide 120 divided by 1/2. Alright, so now I'm going to go back to elementary math, multiplying fractions, dividing fractions, keep it, change it, flip it, right? So it's going to, instead of being 120 divided by 1/2, it's going to be 120 times 2. So that will give us a secondary winding voltage, 240 volts. What will our secondary line voltage be?
240 volt.
Absolutely. Why is that?
It's parallel. It's delta.
Delta. All right, so we're going to hook that up. So H2 to C, H1 to A, H2 to A. All right, what is this?
That's a corner ground. Whoa. Corner ground.
Mm-hmm. Alright, our secondary line current is 361.27. What would our winding current be? Not the same, Gary.
Times.
Alright, so just remember this, that your line voltage or line current, if it, depending on what it is, in a delta, your line current is going to be bigger than your winding current, right? Because it's the whole kit caboodle, right? In a Y, your line voltage is going to be greater than your winding voltage, right? Okay. All right, y'all do the rest of these worksheets here, and the next 2 lessons in homework.
I appreciate you getting.
Hey. I want to shake your hand again.